Let us derive magnetic vector potential from the vector Poisson's equation for a very long current carrying conductor. So let us say that there is this conductor which is carrying current, and the direction of current is along z axis. The radius is a. So the current density will be in z direction and its other component will be 0. So j is equal to jz az, where jz is equal to the total current divided by the area, the cross section area. So this cross section area is pi a square. So if this wire is carrying total current I, so this is the current density, the volume current density, and J x is equal to J y is equal to 0. So from the Poisson's equation, you can see that Ax will be equal to 0 and Ay will be equal to 0. Only Az component will be there, and Az could be find out because we know Jz by simply comparing with the counterpart, which is the scalar potential. Now for a line charge lambda, you know that the scalar potential at a point r from the line charge is given as phi is equal to lambda by 2 pi epsilon naught natural log r naught by r, where r naught is some point, reference point which is very far away. So phi is simply lambda by 2 pi epsilon naught natural log r naught minus natural log r. Since we will be dealing with the differentials only, by that is by differentiation only, so this constant will not be of much use. So I can just write that phi is equivalent to minus lambda by 2 pi epsilon naught natural log r. Now for this case, when this was a line charge, we have this potential. Now a line charge can be written as volume charge into the area. So this is what we will require. So for this, the Poisson's equation was del square phi is equal to minus rho by epsilon naught, and lambda was equal to rho pi a square, or rho was equal to lambda by pi a square, and we have the value phi is equal to minus lambda by 2 pi epsilon naught. So you see, on comparing this with this equation, dou square by dou z square is equal to minus mu naught jz, where jz is equal to I by pi a square. I can write directly az is equal to minus pi a square jz over, and of course into mu naught epsilon naught 2 pi epsilon naught. So I have just written directly on comparing this. I have replaced lambda with rho pi a square, and rho is equivalent to jz here. So lambda is rho pi a square and rho is equal to jz, so this is actually lambda. So in this way we have just directly found az by knowing the solution of the scalar potential. So it is easy now because we know that we can write now the total vector potential A is equal to ax plus ay plus az, where now this is equal to 0, this is equal to 0, and only this quantity is there, and it is equal to I can write it as mu naught upon 2 pi I, because now jz into pi a square is simply the total current I natural log r. So and this direction is az. So this is the vector potential. Now we can find the field is equal to del cross a, where bx will be equal to dou by dou x, so dou by dou y az minus dou by dou z ay. Now this is equal to 0, only this quantity will be there, and it can be written as I over 2 pi mu naught y by r square, where this r is actually equal to x square plus y square. So I have just done the differentiation, this differentiation. So, and by will be equal to dou by dou z of ax minus dou by dou x of az. Again this will be equal to, and of course it will be minus sign here and plus sign here, I by 2 pi mu naught x by r square, and bz will be equal to dou by dou x ay minus dou by dou y ax equal to 0. So you see that the magnetic field will be simply mu naught I by 2 pi minus y ax plus x ay over r square, or I can write it in the cylindrical coordinate form. This can be written as mu naught I by 2 pi 1 by r a phi. If you have seen my lectures on curvilinear coordinate system, then you can easily transform this into cylindrical form, and you will find that this total quantity is equal to a phi by r. I will not explain it here. If you have any doubt, you can revisit my lecture on cylindrical coordinate system, and it will be easier. You just have to replace y with r sin phi, x with r cos phi, and similarly you have to replace the ax and ay with the required components, which I have explained in my lecture on curvilinear coordinate system. By putting all these values, you will find that you are able to get this quantity. So in this way we have found the magnetic field due to a long wire, outside a long wire, and in this first we found the vector potential by simply comparing the solution for a non-scalar potential equation. So in this way we can utilize our knowledge of electrostatics for solving various equations and questions of simple geometries by first finding the vector potential, and from that we can find the magnetic field. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel and join our Telegram group, whose link is given in the description of this video. Thank you.